Hello, everyone. I hope that you're doing well. Thank you for your continued support of RT Tips by DW. Also, I hope you're enjoying the RT Test Tip Tuesday segment. And I'm going to try to begin a new segment, RT uh, tutorials. So we'll look at that moving forward. Today, what I want to do is go over a little bit of, or get a starting point for my students, my cardiopulmonary anatomy and physiology students, get them started on the cardiopulmonary case study that's been assigned to them. They roughly have about a month to get it completed because it's heavily involved with uh, oxygen content calculations and so forth. So just kind of want to kind of review that. In our cardiopulmonary anatomy and physiology class, we've gone over a significant amount of information that spans from the basic respiratory anatomy, the overall functionality of the respiratory system. We've broken it down and gone over in detail over the upper respiratory system, the lower respiratory system. We've also talked about pulmonary circulation, cardiac circulation. Uh, uh, we've touched a little bit on left and right heart failure. We started off the semester with making sure that you can pretend that you're a red blood cell and that you should be able to pretty much uh, course your journey through the heart, through pulmonary circulation and then back out into systemic circulation and ultimately back to pulmonary circulation. So we've done that. We've also talked about, again, mechanics of ventilation, getting air in and out of the lungs. We've talked about things such as shunt, dead space. And this case study really helps to bring about everything that we've learned up to this point, and then what we will also learn beyond, because we have arterial blood gas interpretation coming up toward the very end of the semester, which is right here upon us. We've only got about 4 weeks left, and we also uh, have gone over diffusion, we've gone over oxygen transport, CO2 transport, and all of the calculations that are involved with that. We've mentioned those in lecture. You've been tested on some of the components of those exams, and this case study gives you an opportunity to really put in action what you have learned over the last semester. So before we go through the cardiopulmonary case study, and first and foremost, I should mention this is a borrowed assignment. I wish I could take credit for the creation of such a fantastic such a fantastic assignment. However, this is a borrowed assignment. May change some numbers here and there, but ultimately it is a borrowed assignment. But nonetheless, a great assignment to get you involved uh, in all of the content that we've covered this semester. So before we dive into the case study, and again, I'm not going to go over the entire case study. My goal is to just get you started, so that because this is due here in just a couple of weeks, and you all will have time. But and hearing some of your thoughts and frustrations with even getting started, I thought I might could point you in the right direction. So before we get started and looking at the initial components of the case study, let's review some of the formulas that you're going to need to be able to work out this case study. So we'll start off with the gold standard for the computation of cardiac output. Cardiac output can be denoted by the QT that you see here. We have cardiac output equal to VO2, our oxygen consumption, minus or divided by the arteriovenous content multiplied by 10. Uh, do keep in mind uh, uh, your units of measurement when you're going through each of these calculations. Uh, we can change up that fic formula uh, to help calculate the AV difference. That's going to be important, and I'll discuss that a little bit more in detail moving forward. We also have the content of arterial oxygen formula, the content of venous oxygen formula. Again, pay attention to your units of measurement, also your order of operations with all of these items. So you've got PEMDAS. Remember, anything done in parentheses got to be completed first. If brackets are around it, that's going to supersede the parentheses. So make sure that you do keep in mind your overall order of operations as you go through these. That's going to be helpful. In addition to just being able to compute these items, I want you to also go back and review and pay attention to what is VO2? What is the significance of the arteriovenous difference? If that difference gets bigger, is anything, do you recall anything that we discussed earlier in in the semester about that. Uh, so if it lengthens, if it shortens, you also need to go back and look at the application of that oxygen equilibrium curve, whether or not you're going to get a right shift of that curve or a left shift of that curve, what the overall significance of that is. So all of all of what we've gone over, you get to apply and put in action working into this case study. Oxygen delivery. Also, I want you to pay attention to by knowing one formula, you almost have to know in several cases two or three other formulas to be able to work out that specific formula. For instance, let's say that I didn't give you cardiac output, and let's say that I didn't give you the CaO2, but I've given you some other variables. You've got to calculate your CaO2 as well as utilize that Fig formula to calculate your cardiac output to be able to compute the oxygen delivery. There's also going to be a section of this case study where you're going to be asked to compute 75% of the oxygen delivery. Hopefully, that's not rocket science, and hopefully, you didn't need me to explain this to you. But if you needed to know what 75% of that is, you take your calculated value for your oxygen delivery and then multiply that by 0.75 to get 75% of that. We can also calculate our partial pressure of arterial carbon dioxide. You see the components listed there. In addition to the things that we've covered this semester, we have talked about minute ventilation, respiratory rate or frequency times tidal volume. We've also talked about the effective component of that minute ventilation, which is the alveolar ventilation. So the only effective ventilation you truly have is alveolar ventilation because that's the yes, it is the effective component of the breath or the volume that gets into the lungs. Why is that the effective component? Because that's the component that's going to participate in gas exchange. It gets down into that alveoli, which is going to participate with the capillary network that is surrounding those alveoli. And then you can have ventilation perfusion take place, but specifically the gas exchange that's going to take place uh, at the alveolar capillary bed. Additionally, we can calculate our alveolar air. So we need to make sure that we can do that, the partial pressure of our alveolar oxygen. When you're doing that, remember we talked about very specifically that um, you'll utilize a certain formula or include a factor or not include a factor depending upon what your FiO2 is. And that FiO2, if it was greater than 60 or less than 60. So those are some things that you'll need to make sure that you can remember too moving forward as you utilize these formulas. However, I have taken it upon myself to include the appropriate formula for you for that case study so that in case you happen to fail to remember about that 60% cutoff, whether or not you're going to utilize that factor of 1.2 or not, we can, you know, tried to throw you a bone and help you out. We also need to look at the partial pressure of the inspired oxygen. So remember, you've got to take out that water vapor of 47, and for the purposes of this case study, I do believe we are at sea level, which is going to be 760 millimeters of mercury. As we move on through that, we've also talked about the dead space to tidal volume ratio, or your VD/VT. So the components associated with that are listed for you there. That should be some given information as well. As far as being able to calculate our dead space ventilation. So remember the difference between when you're doing your calculations, if the significance of that dot as it shows up. So that dot being over that lets you know that we are talking about ventilation or minute ventilation, as opposed to where if that dot was not there, then it would just be your dead volume, your dead space volume, which would pretty much be in one breath. So when you're looking at ventilation, remember that's going to be an X amount of breaths over the course of 1 minute. So that's important to remember too. We also have alveolar ventilation. Now there are multiple ways to calculate some of these items that we've talked about. These differ a little bit from what we've talked about in class, but also if you think about these formulas and can rearrange them, then it makes perfect sense to why we would utilize them as such. So to go back over those mechanics of ventilation, we'll also take into consideration that we have covered along with your cardiopulmonary pathophysiology class this semester the differences between obstructive disorders and restrictive disorders. And some of those clinical manifestations that you'll have with that. In addition to that, we'll look at compliant. We've talked about compliance and elastance issues as well, compliance and resistance. So obstructive, restrictive, compliance, resistance type issue, type issues. So we'll look at those items as well. So a couple other formulas that you need to make sure that you can remember is your static lung compliance. Remember, we've got dynamic compliance, we have static lung compliance. You have normal values that you can remember for those for your spontaneously breathing subject. And then remember, if you're utilizing an artificial airway, you bypass the upper air, and you're placing a significantly smaller tube down into the airway. So you're going to have a different set of normal values uh, for your airway resistance and so forth. Um, Moving forward. So static compliance, dynamic compliance, static compliance done under static conditions, that means no flow. So you have to have an inspiratory hold or a breath hold in order to be able to get that plateau pressure variable of the denominator, where you would take the plateau pressure and subtract from that your set PEEP, and then you're dividing all that into your exhaled tidal volume. Uh, so exhaled tidal volume divided by your plateau pressure minus your PEEP. Airway resistance is your peak inspiratory pressure minus your plateau pressure. And that's going to be essentially how you would calculate your trans airway pressure. That's going to be important too when you start to look at some of these items, because there are components toward the end of the case study where if you just conceptually think about what's going on, you really shouldn't have to do a significant amount of math to provide the answer for that. Case in point, trans airway pressure. PIP minus P plat is our trans airway pressure. That's also the numerator portion of our airway resistance, where you're going to take that and divide that by flow. Keep that in mind that your units of measurement are very important. A lot of flows are given in liters per minute. You will need to make sure that you can convert that to liters per second. And you do that by dividing liters per minute by 60. That'll give you your liters per second. So make sure that you can remember that as well. Uh, when we talk about your peak inspiratory pressure minus your plateau pressure, we'll understand that, if I were to ask you specifically when we talk about trans airway pressure in the beginning, that is your airway opening pressure minus your alveolar pressure. Essentially the same thing, you're just being asked it in a different way. Now we're going to look at moving into the summer, where you're getting your intubated mechanically ventilated patients, where you're going to get these measurements. If you do an inspiratory hold with a mechanical ventilator, you will get that plateau pressure. That plateau pressure, as it equals out under no flow, should be equivalent to what the alveolar pressure is. So that's the alveolar component of that. Your peak inspiratory pressure measured at the mouth, that is going to be your airway opening pressure. So we talked about trans airway pressure earlier being your airway opening pressure minus your alveolar pressure. Another way to state that is your peak inspiratory pressure minus your plateau pressure. So I encourage you to go through and pay attention to not just the formulas or the calculations, but what information are you getting from the formula. So you can calculate an oxygen delivery. Well, fantastic. What does it mean? And not listed here, but one of the other calculations that we've gone over is oxygen extraction ratio. So if I can calculate the oxygen extraction ratio, that's fantastic. But I need to be able to utilize that data as well to tell me what it is. Can I calculate a VDVT? Fantastic. What does the VDVT tell me? What may cause it to increase, decrease, and so on and so on. So make sure that you can pay attention to those items. So this may require that you get back into the textbook a little bit and review the information as you go through it, so that you can truly learn what it is that you're performing these calculations for. And also understand these calculations will continue to come back semester after semester, and even well into your preparation for the board exams that you're going to take uh, upon graduation. So now we'll get back to the case study. We'll cruise through this again. This is a borrowed case study. I can't take credit for the creation of it. But it is pretty cool nonetheless. So you do have your cast of characters. I'm going to spare you reading through all that, but nonetheless, you have Dominic Dead Space, Dakota Dead Space, Brennan Bronchus, Vincent Ventilation, Anthony Alveolus, and Riley Respiration. Those are the individuals that we have. So what has taken place is one of those individuals has been murdered, and ultimately through the calculations or the utilization of the formulas, the application of what you've learned, we're going to go through and we are going to determine who ultimately committed the murder. Um, so that's what we'll do. And it tells you here they administer the test to Brennan, who quickly collapses and dies. So now we've got to try to figure out who's responsible for this. So always pay attention to the information that is provided and work through it. So you all, well, My second year students are going to take the clinical simulation exam. My first year students will just challenge the RTE. So there's not a true clinical simulation exam component to that. But nonetheless, if you're preparing for the clinical simulation exam, you're going to be given a scenario and then you select what you feel like is relevant or pertinent. Given that scenario, you're going to information gather, you're going to decision make. But we can talk about that in a different in a different meeting. So we'll get back to the case study. When we go through this case study, it's going to be important for you all to remember that you're given some very important information, vital information throughout the case study that you're going to need for those calculations. So friends, we do need to remember that they have a carboxyhemoglobin level. And when we talk about carboxyhemoglobin level, we've talked about deoxyhemoglobin, oxyhemoglobin, methemoglobin, different types of anemias, carboxyhem. So those are things that we need to make sure that we remember, and we also understand that uh, carbon monoxide will result in carboxyhemoglobin, and carbon monoxide is not a life supportive gas. So we can see that the carboxyhemoglobin levels are 80% in their arterial blood. So 80% with an arterial, but that'll be important. We'll need to remember that here in just a little bit. We also know that the hemoglobin concentration is, so their hemoglobin is 14 grams per deciliter. That's important. We've got to be able to remember that as well. And it says Riley then assumes that at rest, Brennan would have a cardiac output of about 5 liters per minute. That's normal. So at rest, we anticipate that. And O2 consumption, we also went over that that's fairly normal. So 250 milliliters of oxygen per minute, and an arterial PO2 of 100 millimeters. So another way to write that is PaO2 of 100 millimeters of mercury. So that's important information for us to be able to remember. So when we look at the next part of this, it says that she quickly utilizes the Fick principle to calculate Brennan's normal arterial mixed venous oxygen content difference, or the CaVO2. So this is where you're going to have to pay attention because as we've gone over everything in class, we've talked about how to calculate, and I even told you that you would have to calculate the CaO2 and you'd have to calculate the CVO2, and then from that you could subtract the two values together and or from each and come up with your arteriovenous content difference. And going based upon that, you all may go down the road of calculating your CaO2 and CVO2, uh, but you would likely find that you don't have enough information per se to be able to calculate those items with utilizing those two formulas. So now we've got to revert back to the Fick principle or the Fick equation. So if we look at the Fick equation being QT is equal to VO2 divided by your CaVO2 difference multiplied by 10. Multiplied by 10, and this will be CaVO2 in parentheses. So by understanding the Fick principle, we can manipulate this formula, because are we given a oxygen consumption or a VO2? Yes, we are. Are we given a cardiac output? Yes, we are. We're not given the AV. So if you have two known variables, you can switch this formula around to figure out what you need to. So we need to figure out what the CaVO2, and you have to excuse my handwriting, the CaVO2 difference is, and that's going to be equal to our VO2 divided by our cardiac output. So then, if you take 250, and I don't think I can write on the outside of the screen, so I have to keep everything. I don't have enough blank space, so I'll try to write a little bit neater if I can. So our AVO2 difference is going to equate to 250 millimeters of mercury, not millimeters of mercury, 250 milliliters per minute. And I'm going to run out of space there, but that should be per minute divided by 5 liters per minute. Now, if you do the math on this, this is going to equate to it'll come out to be 50 milliliters per liter. So 50 milliliters per liter. If you look down here, so some of you may run into writing down 50 milliliters, or you might write 50 here, but that would be wrong because the answer, the unit of measurement that is provided here is in milliliters of oxygen per deciliter. So you got to go back up and remember that in order to convert this to milliliters per deciliter, if you're multiplying down here by 10, you're going to have to divide 50 by 5 to convert to milliliters per deciliter. Excuse me, divide it by 10. The answer is 5. Divide that by 10, and the answer is 5 milliliters per deciliter. So then you can write 5 on that line there. So now it says to calculate Brennan's CaO2 in the presence of 80% carboxyhemoglobin. Well, if we look at this front, and we know that the formula for CaO2 is, I'm going to write it here because I'll run out of space shortly. CaO2 is equal to hemoglobin times 1.34 times SaO2 in parentheses plus PaO2 times 0.003. Do we have the values that we need to plug into that? Well, we're not quite given an SaO2. We're told that the carboxyhemoglobin level is 80%. So if our carboxyhemoglobin saturation, if you will, is 80%, then that means, and we're looking to complete for 100%, then the rest of it would be oxygen at 20%. So our SaO2 for oxygen is essentially 20%. So we can take our hemoglobin of 14, multiply that by 1.34, multiply this by, and that should be 4. My pen dragged, so it's a 4, not a 9. 14 times 1.34 times our SaO2, which we figured to be 0.2. And we know we're going to add to that 100 because that's our PaO2 times 0.003. If you work that out, I've got a calculator right quick. So 14 times 1.34 times 0.2 equals 3.75. This is 3.75. And then if we remember, we've got to add. So then 100 times 0.003 is 0.3. So now you've got to take the two of those and add those together. So plus 3.75 gives us a CO2 in the presence of 80% carboxyhemoglobin of 4.05 milliliters per deciliter. If you all can remember, now you need to remember what is a normal CaO2, content of arterial oxygen. And if you can remember, we talked about that. Your normal arteriovenous content difference should be 5, which if you're going off, you might would think, okay, so we're 5, that's normal. But now if we begin to look at our CaO2 and remember that our normal oxygen content difference is the two numbers that we utilize there is 20 and 15. That gives us our normal of 5. So our normal CaO2 should be 20, while our normal CVO2 should be 15. So our CaO2 we've calculated at 4.05. That is significantly less than what is considered to be normal for that. So the very next question is going to ask you, did Brennan die of carbon monoxide poisoning? If you have more carbon monoxide than you do oxygen within your blood, and you can see that that is significantly less than what we would consider to be normal, what do you think with regard to that? So that's as far as I'm going to work on this case study. You've got enough now, and I've given you all the formulas that you need to plug and play as you move through the remainder of the case study. I hope that you found this to be relatively helpful. Thank you for your time and attention, and good luck as you complete the case study. Have a good day.